Hi everyone, welcome to this channel. Today we will start with engineering mathematics with linear algebra. Before proceeding to the matrices and determinants, I would like you to remind few important results in linear algebra. Okay. So Descartes' rule of signs says we cannot have total number of positive roots exceeding the number of changes of signs in fx. Similarly, we cannot have total number of negative roots exceeding changes of signs in f of minus x. Say we have fx as 2x raised to the power 7 minus x raised to the power 5 plus 4x raised to the power 3 minus 5 is equal to 0. So obviously this is positive. So 1 change, 2 change, 3 sign changes are there. So 3 changes. If we write f of minus x minus 2x raised to the power 7 plus x raised to the power 5 minus 4x raised to the power 3 and minus 5. Okay, 1 change, 2 change, just 2 changes. Okay, so this means fx cannot have more than 3 positive roots and fx cannot have more than 2 negative roots. And if equation has at most p positive roots and at most q negative roots, then the equation has at least n minus of p plus q imaginary roots. So in this case n is 7 because the order is 7 minus this is p, this is q. So 3 plus 2 5 is equal to 2 imaginary root. So this particular equation has at least 2 imaginary roots. Okay, so next is relation between roots and coefficients. If we have an equation of the form a naught x raised to the power n plus a1 xn minus 1 plus a2 xn minus 2 plus and this equation has alpha 1, alpha 2, alpha 3 and alpha n as its roots. So we have summation of all the roots as equal to minus of a1 by a naught. Also summation of product of every possible pair of roots will be equal to a2 by a naught. Again a3 by a naught minus a3 by a naught. Hence alpha 1, alpha 2, product of all the roots will be equal to minus a1 by a naught. This is same as this one. And sum of all the roots will be equal to okay, wait. Sum of all the roots is minus of a1 by a naught and product of all the roots will be equal to minus 1 raised to the power n an by a naught. Okay, I was wrong. So now this is equal to this one. Okay, next is if we have a quadratic equation ax square plus bx plus c. So we'll have sum of its roots as minus of b by a and product of its roots as c by a. If we have cubic equation ax cube plus bx square plus cx plus t is equal to 0, then alpha 1 plus alpha 2 plus alpha 3 will be equal to minus of b by a, and product of summation of product of every possible pair of roots, sum of product of every possible pair alpha 3 will be equal to c by a, and product of all of its root will be equal to minus d by a. Let's erase this all, or we can move to next page, I think. Yes. So let's move on to matrices. You all are familiar with the matrices. So a system of m cross n numbers arranged in the form of rectangular array having m rows and n columns. So m cross n, where m is number of rows and n is number of columns. Okay, so first type of matrix is square matrix, m cross n matrix, for which m is equal to n. M is equal to n. Okay, so in this case you can write m cross m equal to n cross n if this is a square matrix. Okay, next is diagonal matrix. So in a diagonal matrix is also a square matrix in which all the elements except the leading diagonal elements are 0. Okay, say this is a diagonal matrix. So we can have, okay, this is a diagonal matrix. Okay, so in a diagonal matrix, minimum number of zeros of order n will be equal to n into n minus 1. In this case n is 3. Okay, 3 into 2 will be equal to 6. So minimum number of zeros in this diagonal matrix will be 1, 2, 3, 4, 5 and 6. Okay, so next, if we multiply two diagonal matrix, we will get a diagonal matrix. Say this is A, and we have one more matrix, say 2 minus 1, say minus 1 again, okay, or minus 2. This is P. So A into B, my matrix will be 2, 0, 0, 0, 2 into -1, -2, 0, 0 again, and 7 into -2, -14. Okay. So again, this is a 3 cross 3 matrix. Okay. So next is a scalar matrix. Scalar matrix is a matrix, diagonal matrix in which all the diagonal elements are equal. Three. Okay. This is a scalar matrix, or in general you can write okay, this is a scalar matrix and it is also a diagonal matrix. Next is identity matrix. So diagonal elements are 1 and non-diagonal elements are 0. So this is a identity matrix. Okay. We have some properties of diagonal matrix. If we have to find this matrix inverse of a diagonal matrix, then we will have again a diagonal matrix with reciprocal of these elements 1 by 2, 0, 0, 0, 1 by 7. So to generalize, one by A, 1 by A, sorry, let's say the B and C. So B, C, 1 by B and 1 by C. Okay. So inverse of a diagonal matrix will simply take the inverse of the diagonal elements. And if it is n, if we have to find matrix raised to the power n, we will have A raised to the power n, B raised to the power n, C raised to the power n. Okay. Again, eigenvalue of a diagonal matrix will be simply the multiplication of product of all the diagonal elements, means A okay, eigenvalues now. So eigenvalue of values of diagonal matrix will be simply the diagonal elements A, B and C. And if we have to find the determinant of a diagonal matrix, then it will be product of the diagonal elements. Okay. So next is a triangular matrix. Sorry, I'm new to this application actually. I think we can change the color of the pen. Yes. Say blue. Okay. Okay. So again, okay, this is a upper triangular matrix. Upper triangular matrix, and this is a lower triangular matrix. In upper triangular matrix, lower of diagonal elements are 0. In lower triangular matrix, we have upper of diagonal elements are as 0. Here determinant will be, if it is A and if it is B, determinant of A will be equal to product of leading diagonal elements, and here again product of leading diagonal elements. Okay. Next is idempotent matrix. So in idempotent matrix, we have A square is equal to A, means if we multiply a matrix to itself, it will result into itself. Okay, and determinant of A is either 0 or 1. 0 or 1. For example, we have an identity matrix. So we know that if we multiply an identity matrix to itself, it will result in a identity matrix. Next is involuntary matrix. Involuntary matrix. Here, a matrix multiplied to itself will result in a identity matrix. Okay. Again, we have a simple example. An identity matrix is also an involuntary matrix. Okay. So next is nilpotent matrix. Nilpotent matrix. A matrix is said to be nilpotent of class X if X is the smallest index, which makes a raised to the power X is equal to 0. I repeat, A is said to be nilpotent of class X if X is the smallest index, which makes a power X is equal to 0. For example, minus a square minus ab. Okay, let us check a square, a into a. Let's move to the next page. a square ab b square minus a square minus ab b square minus a square minus ab. Okay, ab into ab, a squared b square minus a squared b square, 0. Again ab cube minus ab cube minus ab cube, again 0. Minus a cube b minus plus a cube b, 0. Minus a square b square plus a square b square, 0. Okay, so here a square vanishes. A is not equal to 0, but a square is equal to 0. So this matrix is nilpotent of the index 2, or this matrix is nilpotent of class 2. Okay, so next we have singular matrix. Singular matrix. If we have determinant of a matrix as 0, then this is a singular matrix. Okay, so 0 is an eigenvalue of a singular matrix. Why? Why? Because product of eigenvalues of a matrix A is equal to its determinant. So if determinant is 0, means product of eigenvalues is 0, then one of the eigenvalues must be 0. And if matrix is singular, its inverse does not exist. Why? Because we have A inverse as 1 by determinant of A into adjoint A. So if this vanishes, that means A inverse does not exist. Okay, so next is symmetric matrix. In symmetric matrix, A transpose is equal to A. For example, this is a symmetric matrix because this is also equal to A transpose. Okay, and skew symmetric matrix, say 0 or minus 2 to 0 will be equal to minus of A transpose, or in skew symmetric matrix, A transpose is equal to minus of A. Look here, if A is 0 minus 2 to 0, then A transpose will be 0 minus 2, 2 and 0. And if you multiply it by negative 1 minus 1, then we will get A transpose is equal to minus A. Okay, so in symmetric matrix we have real eigenvalues, and for skew symmetric matrix we have eigenvalues as either purely imaginary or 0. Okay, any matrix A can be expressed as the sum of symmetric matrix and skew symmetric matrix. Means A is equal to where this is symmetric matrix and this is skew symmetric matrix. Okay, so next is orthogonal matrix. Okay, in orthogonal matrix we have A into A transpose as identity matrix, or A transpose is equal to A inverse. Okay, so if A matrix is orthogonal, then its inverse and transpose are also orthogonal. Its determinant is equal to plus or minus 1. Determinant A and determinant A transpose will be equal to 1. If lambda is an eigenvalue, then 1 by lambda is also a eigenvalue. Okay. See, if if we know that this is an orthogonal matrix, then it has determinant as plus or minus 1. But if we know that a determinant has a value plus or minus 1, then it may or may not be orthogonal. Okay. Miss, this is true only if we know that A is orthogonal. But if somehow determinant of A comes to be plus or minus 1, then that doesn't mean that a matrix is definitely orthogonal. Means it may or may not be orthogonal. And yes, do check my Telegram channel. I will provide the link in description below. I will be providing handwritten notes of each lecture, so please do visit. Okay. So next is complex matrices. Let's change the color. I hope my handwriting is legible and you are getting me. Okay. First is Hermitian matrix. Hermitian matrix. Okay. So A theta is equal to A. What is theta? Theta is transpose plus conjugate. Transpose plus conjugate. Example: A, B plus IC, B minus IC and D. Okay, if you first take the conjugate of this matrix and then transpose, you will get the same matrix again. Okay, so here in Hermitian matrix, do note that diagonal elements are necessarily real. Okay, next is skew Hermitian matrix. Okay, skew Hermitian matrix. A theta is equal to minus A. So example, okay, minus 2 minus I, 2 minus I. Okay, so here diagonal elements of a skew Hermitian matrices are either purely imaginary or real. See, okay, and eigenvalues of a Hermitian matrix are real. Eigenvalues real, and for a skew Hermitian matrix, eigenvalues are purely imaginary or 0. Okay, so we have some few properties of complex matrices. A plus B theta is A theta plus B theta. AB theta is B theta A theta. So here too, every square matrix A can be expressed as the sum of Hermitian and skew Hermitian matrix. So A is equal to A plus A theta by 2 plus A minus A theta by 2. This is Hermitian matrix and this is skew Hermitian matrix. Okay, we will quickly go through minors, cofactors and adjoint. Okay, so this is a matrix. So minor if we have to find minor A to 1, then what we'll do is, so answer will be A12, A13, A12, A13, A32, A33. Okay. Similarly, if we have to find minor A32, minor A32, so we're left with A11, A13, A21, A23. Okay. So A32 is equal to A11, A13, A21, A23. And cofactor of element Aij is given as minus 1 raised to the power I plus j Mij, where Mij is the minor. So in this case, if we have to find cofactor A32, then we will have minus 1, 3 plus 2, 5 and Mij, A11, A13, A21, A23. Okay. And for adjoint, when all elements of a matrix A are replaced by its cofactor, then transpose of that matrix is known as adjoint of matrix A. Okay, let's clear this, erase all. So you must have known how to find out determinants. Okay, so for determinant A1, B1, C1, A2, B2, C2, A3, B3, C3, if we expand along this row, so A1, B2, C3 minus B3, C2 minus B1, A2, C3 minus C2, A3 plus C1, A2, B3 minus B2, A3. Okay, this is how we find determinants. We have few properties of determinants, such as value of determinant does not change when rows and columns are interchanged. That is, determinant of A transpose will be equal to determinant of A. If any row or column is completely zero, means a row vanishes or a column vanishes, then determinant will be equal to 0. And if any two rows or columns of a matrix are identical or proportional, then means dependent, then also determinant of A will be 0. If any two rows or two columns are interchanged, the value of the determinant is multiplied by minus 1. Say minus 1 to the power m delta. What is m? Number of times two rows or columns are interchanged. Okay. So what if we multiply a scalar to the matrix? Then every elements in the matrix will be multiplied by scalar k. Okay. But in the case of determinant, if we multiply k to the determinant, then just a row or one column will be modified. Say here just one row. Okay. Or you can say this as equal to k times A. Okay, determinant A. Okay. Next, if we have to find inverse of product of AB, then this will be expanded as B inverse A inverse. Again, if A beats C inverse, will be equal to C inverse, B inverse, A inverse. Okay. So if A is a n cross n non-singular matrix means determinant of A is not equal to 0. Then A transpose, inverse of A transpose will be equal to transpose of A inverse. Okay. And if it is complex, then we can write like this. Okay. So for a 2 cross 2 matrix, we can simply, if we have to find inverse of this matrix, then we can simply determinant of this matrix, this will be equal to AD minus BC, and adjoint of this matrix, Adjoint of A is D. Adjoint of B is minus B, minus C and A. Okay. So what we did is we just replaced the elements, all the elements of this matrix by its cofactor, and then took the transpose. Okay. It has already been 40 minutes. That's all for today. I will probably need one more lecture to cover all the points in matrices and determinants. Okay. Then we will practice. Then we will practice selective problems. Okay. See, maths is all about practice. The more you practice, the better you get. Okay. So, bye. See you in the next lecture. Thank you.